So welcome. We have basics of turbulent flow in the last lecture. We have looked at scales of eddies, what kind of eddy sizes are there, smallest eddies, largest eddies. We had used all that to calculate something like universal velocity profile, which is applicable across all spectrums of flows. It is flow near the wall. That is the advantage. That is the applicability of universal velocity profile. That wall can be anywhere. It can be in a pipe, it can be in a jet, it can be in a plane, it can be in stir tanks, anywhere, in any application, wherever there is a flow parallel to the wall, we will have universal velocity profile being applicable. And we got that straight from equation of motion, the microscopic balances for turbulent flow. And so that's the beauty, and that's the applicability, and that's the advantage of studying microscopic flows. Any macroscopic quantity we can calculate starting from these microscopic equations, and then I'll give you some more examples in this class. So let's get started. This is where we are in our course. We are on point number 7, right? Just to get you started, just to quickly revise, what are the smallest turbulent scales called? Why are they called as smallest scales? How is eddy viscosity related to velocity and length scales of the eddies? Till what values of Y plus do we have laminar sublayer and buffer layer? This is from universal velocity profile. Moment you say Y plus and Vx plus, you are talking about a universal velocity profile. Okay, just to quickly recap, we have talked about laminar flow, we have talked about turbulent flow. These are the equations that we are having. This is an additional term, turbulent viscosity, and turbulent viscosity depends on the size and velocity of the eddy. It is not a physical property. It varies with location. It could vary with time as well. Mathematical models describe how mu-t varies with a local velocity field. They could be algebraic equations, they could be partial differential equations. These are called as turbulence model. This was there in the last lecture. I'm just still trying to revise quickly the last lecture. And a numerical solution is required to get a velocity profile, right? And this numerical solution is called as computational fluid dynamics, CFD for short. So you should be very if you have to do CFD simulations, you need to be able to solve these partial differential equations. You need numerical techniques, you need a lot of computational power to actually solve. And at the end of the class, or at the end of this lecture, I will show you some examples where computational fluid dynamics is used for which involves solving this equation along with turbulence model for a variety of situations. Okay? We'll talk about that a little bit towards the end. Before that, let's talk a little bit about boundary layer. So what we are going to talk about is steady state, uniform flow. Uniform flow means velocity is constant across the spectrum, across the y direction. This is our y direction, this is our x direction. This is our x direct. X is here actually. X is not here. Our y is here. Origin is here. This is our origin. So this is our x. This is our x. Okay. This is our origin. So plate surface we can describe as y equal to 0. That's the plate surface. So now if you think about boundary layer, if you plot velocity profile at this location, okay, you will find that velocity is small here. Why? Because there is a no slip condition here. Why? Here velocity is large because it is a free stream. Velocity is v0 here, far away from the plate, right? And it varies gradually from 0 to this value of v0. So velocity profile is something like this. If you go further, velocity profile is something like this. If you go further, velocity profile is something like this. So we can define point of, let's say, 95% of v0, where that is reached. Let's say that is reached here at this location x. At some other x location, the point of 95% velocity is reached, let's say here. At some other x location, the point of x velocity, 95% of v0 is reached here. So this distance is called as boundary layer thickness. It is denoted by a symbol delta, and you can see that because we are talking about flat plate, from the start of the plate, delta is a function of x. At x is equal to 0, delta is 0. As you go along x, delta increases. Delta is a function of x. What I want you to do is calculate velocity profile and friction factor for this plate. Okay. Here is how we do it. First of all, equation of continuity, and flow is 2 dimensions. So this Vz is 0. Then Vz by del z is 0. Where is the Vz direction? Vz direction is perpendicular to the screen. Perpendicular to the screen at this point. Z direction, perpendicular to the screen, going in or coming out of the perpendicular to the screen. Z direction. There is no velocity in the z direction. It's a uniform flow. So del Vz by del z is 0. So equation of continuity tells you del Vx by del x plus del Vy by del y. Let's scale these variables, and the scaling variables that we want to use are like this. So for example, Vx we want to scale. What do we mean by that? We mean that Vx should vary from 0 to 1. Right now Vx is varying from 0 to V0, but I want it to vary from 0 to 1. How will I do that? Is if I divide by V0. So we call that as a scaling variable for Vx is V0. So if I divide by this scaling variable, the dimensionless Vx will change from 0 to 1. What is the scaling variable for x? How does x change? X is equal to 0 here, x is equal to L here. But I want the dimensionless variable x to vary from 0 to 1. How will I do that? Is if I divide x by L. Then the dimensionless variable, let's say x bar, will vary from 0 to 1. What is the scaling variable for y? Where is the flow changing? Flow is changing only in this region. Beyond this, it is practically V0. That's not of our interest. We want y to change at this location. We want y to change from here to here. We want to make that y dimensionless and make it go from 0 here, 1 here, 0 here, 1 here, 0 here, 1 here. Only way we can do that is if I scale the variable y with respect to delta, which means we are going to divide by delta. That's the meaning of the word scale, scaling the variables. Okay. What variable should we take for Vy? Well, right now let's just put it as Vy naught for now. Let's see what that is. Okay. And make these equations dimensionless. So first of all, we'll make continuity dimensionless, then we will use Navier-Stokes equation and we'll make it dimensionless. Remember, we are talking about laminar flow just now. We'll talk about turbulent flow a little later. Laminar flow. Okay, scale the continuity equation, which means, so we are, if we have dvx by if we have del Vx by del x plus del Vy by del y equal to 0. Vx we are going to scale, which means we are going to divide by V0, Vx by V0, multiply by V0. This Vx by V0 is now a dimensionless variable, which we are going to write as Vx bar. Scale the x, multiply and divide by L. So x by L is a dimensionless variable now. We are going to call it as x bar. So Vx bar is going to vary from 0 to 1. Let me just write that. Vx bar varies from 0 to 1. Is that clear? X bar varies from 0 to 1. We can make y also dimensionless, Vy also dimensionless, Vy by Vy naught, that will give you del Vy bar. This should be Vy bar. Make that change. Okay, let me put that change there. Just let me correct. So I made that correction now. Right, Vy by Vy naught. That's our Vy bar. Vy bar now will go from 0 to 1. Y by delta is going from 0 to 1. Y bar. Okay. I can take out this V naught. It will be V naught by L del V x bar by del x bar. Vy naught by delta del V y bar by dy bar. Delta y bar. Okay. Now there are two terms in an equation, and if two terms are there in the equation, both terms should have same order of same magnitude. Look at the brackets. Look at the brackets. Look at the dimensionless variables. The dimensionless velocity gradient dvx by dx del vx bar by del x bar, this is of the order 1, 0 to 1. This is of the order 0 to 1. If that is the case, these coefficients must be of the same order of magnitude or nearly the same. So that will tell you what is the scale for Vy naught. So V scale for Vy naught is V naught into delta by L. And you see delta can be small. Delta by L is very small. Delta is small. Remember we talked about laminar sublayer and buffer layer. How small they were? 5 microns, 50 microns, of that order, 30 microns, 100 microns. They are that small, that small. So delta by L is far less than 1. So Vy naught is far less than V naught. What does that mean? What does that mean? Think about this velocity profile. What does dvx by dx mean? The velocity, let's say at this location, at the same value of y, we are trying to look at how the velocity is different. Let's put this arrow, this cross here. Let's take 2 points. Let's not put cross we have already put. Let's take 2 points. Let's say point here, and at the same y, because we want del vx by del x, same value of y, so same horizontal level, I take another point which is having a separate distance, different, which is having a different value of x. You see velocity is changing. Here it is practically v naught, here it is less than v naught, so velocity is reducing. Remember, velocity is reducing. It is as if the flow is compressed. That del vx by del x is going to lead to flows in the y direction, and the scale magnitude of that y directional flow is given by this expression. So continuity equation tells you that if you know delta, if you know L, what is the value of velocity in the y direction that can be generated straight from continuity equation, nothing else. Let's go forward. Equation of motion now, Navier-Stokes equation. Let's take in x direction. Okay, let's take in x direction. Right, here's a little, so do this for yourself. Okay, Vx, make it dimensionless. Del Vx by del x, make it dimensionless. You will multiply, have to multiply by V naught square by L. Okay. Vy, make it dimensionless. Vx by Vy, del Vx by del y, make it dimensionless. You will have Vy naught, V naught by delta, and Vy naught, this Vy naught is V naught delta by L. So it is, next it is substituted here, V naught square by L. dp by dx, p naught by L, right? Mu del square Vx by del x square, make it del square Vx bar by del x bar square. You will have to multiply by V naught divided by L square. Del square Vx by del y square, make it del square Vx bar by del y square. You will have to multiply by V naught by delta square. Get this yourself, make sure you get it yourself, only then go forward. Okay, so this we have substituted now. V naught square by L we can take out common, right? That's what I have done here. So I get this mu V naught, L square I have taken out common, so I get this term L square by delta square, multiplied throughout by L divided by rho V naught square. So I get this on the left hand side, convective terms, P naught by rho V naught square, like 1 by Euler number, mu by L rho V naught, L square by delta square. Now here is the deal. Here is the deal. Okay. What is delta by L? Delta by L is small. So L square by delta square is very, very large. What can we compare? What can we say about the magnitude of these two terms? Magnitude of this term is negligible as compared to the second term. I can even neglect that. What does it mean? It means that compressive stresses del square Vx by del x square. Where, remember, del square Vx by del x square. What is that? Del square Vx by del x square. Del square Vx by del x square. That's a compressive stress. Normal stress. Remember where it has come from? It is coming from mu del Vx. Mu, it is coming from tau xx. Del by del x of tau xx. X directional equation of motion. Del by del x of tau xx. Tau xx is dvx by dx. It's a compressive stress. What it only means that compressive stress is very small as compared to shear stress, del square Vx by del y square. Where is that coming from? That's coming from tau yx. Shear stress. It just means that the shear stress is far, far larger than the compressive stress. Shear between the layers is very large. As compared to the compressive stresses, shear. That's the meaning of this equation. And we have got that straight from Navier-Stokes equation. Nothing else we have used. Let's go forward. Okay. Now look at the left hand side. Left hand side is of the order 1, 0 to 1. Now this pressure gradient is usually not important. Why? Because it is a plate is open to atmosphere, so density is practically constant. It is a very small pressure gradient. So actually it is not P0, it is actually the pressure gradient that we should use for making it dimensionless, and the pressure gradient is usually small. So this is an important term, but it is not necessarily the driving term. What is driving is the convection. The left hand side is 0 to 1. So the right hand side, the viscous stresses, they have to be considered. They cannot be neglected. Why they cannot be neglected is because there is a gradient. There is a gradient, and then there is a stress, viscosity, tau w. All those things are there. So viscous stresses cannot be neglected within the boundary layer. If they cannot be neglected within the boundary layer, that means this term, let me use another color. That means this term has to be important, has to be considered. If it has to be considered, and the dimensionless variable is of the order 0 to 1, that means this mu L rho V naught L square by delta square must be of the order 1, because left hand side is of the order 1, the right hand side must also be of the order 1. So the coefficient must also be of the order 1, which means delta by L must be equal to square root, must be of the same order as square root REL. Look at this, REL, Reynolds number based on length of the plate. REL based on length of the plate. Now we have defined so many Reynolds number based on pipe diameter, based on turbulence, based on Y plus, based on particle diameter. Now this is yet another Reynolds number, L rho V naught by mu. And what a powerful equation, what a powerful result we have got. Delta by L is of the same order as 1 by square root REL. Without knowing anything, just from this equation, we have said that delta by L must be same order of magnitude as 1 by square root REL. So if it is, let's say, water, rho by mu is 1000. Let's say V naught is 1, rho by mu is 1000, 10 raised to minus 3, so 10 raised to 6. So if plate is 1 meter, and its water velocity is 1 meter per second, REL is like 10 raised to 6. Square root REL is 10 raised to 3, 1000. 1 by square root REL is 0.001. Delta by L is 0.001. And if plate length is 1 meter, delta is 1 millimeter. Look at the result. What it means, delta is 1 millimeter. Without solving anything, just by looking at Navier-Stokes equation and scaling the variables, we have been able to say that delta is of the order of 1 millimeter for this particular case. Of course, in general, delta by L is proportional to square root REL. Or let me rub this little bit now. I need some space. Delta is going to be proportional to square root REL. I'm going to write proportionality sign. Square root L. You bring L on this side, REL is L rho, so it is going to be proportional to square root L. Not only we have been able to get a magnitude of delta, we also know how delta is going to vary with L. We know delta, suppose L was this much, we will have this much delta. Delta is going to vary as square root length of the plate. That result we have got straight by looking at equation of motion by scaling. That's the importance, that's the advantage of scaling the variables. We come to know so many things about the problem. That's the beauty of Navier-Stokes equations. Let's look at the y direction. Same way, y direction, if you do this yourself, if you scale it yourself, what you will find is that the pressure gradient in the y direction is not there. 0. That's a very important result. Right now we may not know the importance. Delta P by delta Y is 0. That means whatever is the pressure outside, we can say the same pressure is at a particular location of X. Pressure here and 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 pressure here, they are the same. Advantage is that we don't have to worry about the boundary layer when we are talking about the pressure calculations outside. We can just get the outside pressure and then correspondingly we will get the pressure inside the boundary layer as well. That's the advantage. So not very important for us just now, but when you start doing aerodynamics, suppose this is a wing of a plane, there is a boundary layer on the plane. Outside pressure we can get from the wind, we get from the situation where the viscous forces are unimportant. Euler number, Reynolds number is large. We can neglect the viscous terms. We can just use the convective and pressure terms and get a pressure field. Simplified version of the Navier-Stokes equation will give us the pressure field, and that pressure field will be the same as inside the boundary layer. Each sentence, you make sure that you understand each sentence before going forward, because all these are very important terms. So the simplified Navier-Stokes equation is just like this: rho Vx del Vx by del x, Vy del Vy by del y, minus del P del x, Gx is not there, gravitational component is 0, mu del square Vx by del y. Now Blasius was the first person, 1900s, he gave a solution. He found two things. First thing he found is delta by x is proportional to, is equal to 5 divided by square root Rex. Now another definition of Rex is x rho V naught by mu. So at any particular x, if I know the x value, let's say x is 30 centimeters, rho mu V naught we know, so we can calculate Rex, we can calculate square root Rex 5, delta by x is equal to this number. and from there I can calculate the thickness of the boundary layer, and you will see that x is proportional to delta is proportional to square root x. We had got that result here, delta proportional to square root L, right? Okay. Second thing, he said that velocity field can be made dimensionless, Vx by V naught, and it can be made dimensionless by a variable y if I divide by this quantity, or if I multiply by square root V naught rho by x mu, which is really in a sense what it is saying is Vx by V naught is a dimensionless velocity field. It can, so this I can write little differently. I can write this as y by x into root rex. It's a dimensionless y distance. He said that he found that there is a unique relationship between these two variables. This relationship is independent of which x you are looking at. That means the velocity field is self-similar. Look at x, rex is different values of rex. But data is on the same curve. Which means velocity profile, if I make it dimensionless, if I am looking at any x, if I am looking at this x or 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 this x, any x I look at, if I make the velocity field dimensionless by V naught, and if I make the y dimensionless by this distance, in effect what are we doing? Look at this variable once again. Look at this. What are we doing? Rex, square root Rex is like 5x by delta. So this variable is like y divided by 5 delta. So if I make y dimensionless by delta, and if I make Vx dimensionless by V naught, I get a dimensionally similar, I get a behavior which is same for all values of x. That's the beauty of making things dimensionless. Okay. More on these results now. Okay, so what he said is we have to get to friction factor. That's where we are getting. We are going to say Vx bar is Vx by V naught. We'll define a variable zeta, which is this y by x square root Rex. So this graph is now between Vx bar and zeta. Okay. What is tau w? Mu dvx by dy. There is no minus sign. Vx is increasing with y, but it is evaluated at y equal to 0. Rearrange, you will get this expression, tau w as mu v naught square root Rex by x dvx bar by d zeta at zeta equal to 0. What is this value? It is nothing but slope at zeta equal to 0. Slope of this curve. What is the slope of this curve? 0.2, 0.3, slightly more than 0.3. Slope of this curve at the origin. It's like a straight line if I draw at the origin. That's the slope. That slope is 0.332. That's what he found. So you can now left hand side divide by half rho v naught square, you will get F friction factor, but it is at any x location. at any x location, because this is in terms of x. Rearrange, you will get f of x, a friction factor at any x location is 0.664 divided by square root Rex. Friction factor for the whole length of the plate, Fl, is integral 0 to L f of x dx divided by L. Do this for yourself, you will get f friction factor for the whole plate as 1.328 divided by square root Rel. Power of Navier-Stokes equation, power of microscopic balances. We could write it in dimensionless forms. We could get the slope from experiments, of course. We could get friction factor for the whole plate. This is friction factor for the whole plate. F of x is the Fx is the local value of friction factor. Local value of friction factor. Because it is local value of tau w. Tau w. These tau w's are local values. It is value at any x. See, this tau w is at any x. It is dependent on x. These are local values. This is overall for the whole plate. We have averaged it out over the whole plate. Okay. There is another way of doing things that's called as von Karman integral equation. The reason I am doing this, you will see little later. Okay, is von Karman integral equation. Let's talk a little bit about that now. Okay, so imagine this is our plate and this is our boundary layer. This is our plate. This is our boundary layer. We are going to take this control volume shown by this red. Okay. If I write mass balance on this control volume, what we'll get? Mass in, mass out. Let's calculate that first. Mass in is del in is rho Vx. W is the width that is perpendicular to the screen in the z direction. Dy. Vx multiplied by area perpendicular to Vx, that is W dy. Integrated from 0 to delta, this integral is evaluated at x. Same integral I can evaluate at x plus delta x. I will get the mass going out. So this is rate at which mass comes in. It is mass flow rate in. Mass flow rate, let me write that as m dot, mass flow rate in. This is mass flow rate out. Which is larger? This is larger. Out is larger because it is integrated over a larger distance, 0 to delta. Delta is increasing. If velocity profile is self-similar, it is integrated over a larger distance. Flow goes out. That means there is a flow coming in to this control volume at the top surface. Let's write that. That rate would be rate at which mass comes into the control volume from the top surface is going to be equal to out minus in is going to be the rate at which mass comes in. So if I say dm by dx is the rate at which mass enters per unit length, not width, per unit length. Rub this. Let me rub this for a second. Make that correction. Yeah, okay, we can say that it is per unit width, but per unit length also. That's why we are taking dm by dx. So dm by dx is the rate per unit length, per unit width. M is per unit width, m dot is per unit width. So I need to multiply this m dot w and dx. That will tell me the rate at which mass comes in from the top. Now what is the equation? What goes out minus what comes in must be equal to what is entering from top. So I'll get an expression for dm by dx, the rate at which mass enters along the x direction, dm by dx. Why does it enter? Because it has a velocity component perpendicular to the surface. That's the Vy. That's the Vy naught. That's the Vy naught. Remember? That's why mass enters. So you will get this expression. Derive this. Make sure that you get it for yourself. Now on this control volume, can we write momentum balance as well? On this control volume, yeah. So what comes in? Momentum per unit volume. What comes in? Momentum per unit volume is rho Vx. Momentum per unit volume is rho Vx. The rate at which it enters, Vx W dy. W dy, area perpendicular to Vx. Integral from 0 to delta, this integral is evaluated at x. Plus, now this is another important point. W into dx into dm by dx, that was the moment rate of mass entry. What is the velocity? X directional velocity. We are writing a balance in the x direction. What is the velocity in the x direction? V naught. So that's the momentum entering because of the mass entering here. What goes out? Rho Vx W dy. It is evaluated at x plus delta x. So force balance we can write in minus out must be equal to force at the plate. In minus out. This has to be plus. It will be tau w. Dm by dx now. Can we simplify that? Dm by dx. Can we put that? Okay, it's corrected now. So in minus out. In, so this is a positive term. Minus minus. I have just made it so that we can take the derivative. Okay. In minus out is the force, and therefore tau w. Okay. So simplify. Substitute for this dm by dx from this expression. This is what you will get. And if I divide by rho v naught square, I will get d by dx, vx by v naught, 1 minus vx by v naught dy. Make sure that you get this expression. Now another way, again we are making it dimensionless. So vx bar, vx by v naught, eta we are saying is y by delta. So tau w if we say is mu dvx by dy at y equal to 0. Tau w by rho v naught square, we can say mu rho v naught delta dvx bar by d eta at eta equal to 0. Let's call this slope as some value. The slope has some value. Let's call this as beta. Beta, it is the value of this slope. It is like the value of the slope here. Okay. We are not going to use that result. We are going to use something else. And so tau w would be mu rho v naught delta into beta. Now we had this expression. Substitute that vx bar and eta here. You will find that tau w by rho v naught square is d by dx, 0 to delta vx by v naught. This was the expression. Put it in terms of delta and eta. This integral only depends on how dimensionless velocity varies with the dimensionless y by delta. See that here. How dimensionless velocity changes with dimensionless y by delta. The profile. So what is needed is the profile and the slope. These two together allow us to calculate. Let's indicate this integral by alpha. So integral 0 to 1 vx bar into 1 minus vx bar d eta is alpha. So tau w by rho v naught square would be alpha d delta by dx. Now use these two expressions. Left hand side is the same. One is coming from slope at the origin, slope at y equal to 0, and one is coming from the shape of the velocity profile. Equate them together. If you equate them together, you can get a differential equation in delta. Solve that, you will get delta by x as square root 2 beta by alpha rex. Remember the Blasius solution. Blasius solution was delta by x was 5 by square root Rex. That was experimentally observed by Blasius. We are getting the same result now, but based on momentum balance. Only thing we do not know is what is the value of this 2 beta by alpha. If we write in terms of friction factor, tau w by half rho v square, tau w by half rho v square, you can take from here, use this expression. Just make it half here, half, and then half on the other side as well. And simplify. You will get friction factor at any x as square root 2 alpha beta by Rex. Integrate, you will get the friction factor for the whole plate as 8 alpha beta by Rel square root. We still don't know the value of that because we don't know value of alpha and beta. Alpha depends on velocity profile, beta depends on slope of the velocity profile at y equal to 0. But only based on momentum balance we have got a dependence of F versus Rel. F is proportional to 1 by square root Rel. That is the power and that is the beauty of microscopic balances, Navier-Stokes equation. Starting from Navier-Stokes equation, you can get everything that you want. Only thing that remains now is to calculate this alpha and beta. So I'm just going to give you some examples. So if you say that alpha and beta, how we will evaluate? We need the velocity profile. So if I say linear velocity profile, which means Vx is eta, you will get friction factor for the whole plate as 1.15 divided by square root Rel. If you say quadratic, Vx is a eta square plus b eta plus c. If you put eta equal to 0, that is the plate surface, right? Vx bar is 0, so c must be 0. If you take eta is equal to 1, Vx bar is 1, that means a plus b is equal to 1. One more condition we need to find the values of a and b. What is that? Look at this profile. This profile, look at this profile. This profile, this gradient is practically 0 at the edge of the boundary layer. So when eta is equal to 1, when eta is equal to 1, dvx bar by d eta is 0. So if you differentiate this Vx bar, if you differentiate dvx bar by d eta, this would be 2a eta plus b. And if I put eta is equal to 1, 2a plus b would be 0. So 2a plus b is equal to 0. Which means a is minus 1. And b is 1. Sorry, b is, sorry, b is 2. So velocity profile, what is the velocity profile? Vx bar is equal to 2 eta minus eta square. That's the velocity profile. You get that? If you use this to evaluate the values of a and b, sorry, alpha and beta, that's what I mean, you will get friction factor for the whole length of the plate is 1.45 divided by square root Rel. You see, using momentum balance, what have we got? Using momentum balance, using momentum balance, integral equation, we got friction factor versus Reynolds number relationship. That is the power of Navier-Stokes equation. That's the power of microscopic balance. That's why this is a very important part in the syllabus. Let's go forward. Let's start looking at turbulent boundary layer now. So turbulent boundary layer, what we mean is that, let's say this is a flat plate. Let's put that laser pointer. Yeah, so there's a flat plate. Boundary layer here, flows are small here, the velocities are small, so boundary layer is laminar here. But beyond a certain RE, the thickness of the boundary layer increases so much that velocities even inside the boundary layer are high, and the flow can become turbulent even within this boundary layer, which means there will be a turbulent boundary layer here, but within that turbulent boundary layer, very near the surface, we will still have laminar sublayer, we will still have buffer layer, and so on. First of all, let us try to get at what value of this Rex, or at what value of this X or X critical, the flow becomes turbulent. Imagine that for a pipe we had R rho V naught by mu. Just take V infinity. V infinity is like this V infinity. If you want make this change here, let's call this as V infinity now, just so that I have all the values. This is V infinity if you like. Okay. So if you say laminar flow is there till a Reynolds number of 4000, which means Reynolds number based on the radius of the pipe, if I calculate, that will be, let's say, RE of 2000. Now I want that in a pipe RE based on the radius, which means is like I'm saying the boundary layer has become thick equal to the thickness of that or the radius of that pipe. So I'm going to replace this R by delta. So delta rho V infinity by mu is about 2000. So delta V infinity rho by mu is 2000. Delta by X, X rho V infinity by mu is 2000. Now delta by X from Glacier is 5 by square root Rex, so 4.64, more accurate one, X rho V naught. So if you rearrange, you will find that Rex of 1.8 into 10 raised to 5, typically 2 into 10 raised to 5 or 3 into 10 raised to 5, flow becomes turbulent, which means that the critical Reynolds number or the critical length at which the Reynolds number based on this critical value, so XC, critical distance, XC rho V infinity by mu is about 2 into 10 raised to 5. So if it is water, rho by mu is 10 raised to 6. V infinity suppose is 1 meter per second. Then that means XC is 2 into 10 raised to 5 divided by 10 raised to 6. So it is 0.2 meters. So a 20 centimeter plate, if the plate is more than 20 centimeter, 0.2 meters, there will be laminar boundary layer before the 20 centimeters, and there will be a turbulent boundary layer after 20 centimeters. That's the meaning of this critical Reynolds number. Okay, same way we can do if I assume velocity profile. Now in turbulent flow, the velocity profile that I am going to assume is like this. Let me give you that expression. Okay, I need an expression for how Vx bar changes with eta. The expression that we are going to take for turbulent flow is 1/7 power law model. Vx bar is typically 1 minus eta whole thing raised to 1 by 7. Using this, we can calculate alpha. Right? Using this, we can calculate alpha. Alpha, where are we using? We are going to use alpha here. We are going to use alpha here. Tau w by rho v naught square is alpha d delta by del x. Where is that gone? Let me put that here. Okay. So we are going to put tau w. Let's put red color. Tau w by rho v naught square is alpha d delta by del x. This expression tau rho v naught. This expression. What is the other expression? Tau w by rho v naught square is beta. Beta is coming from slope. Mu rho v naught by delta beta. Beta is coming from slope. It is this. So I need the slope, right? That's going to come from experiments for turbulent flow. Okay. So tau w by rho v naught square. In this case, rho v infinity. I'm just using a different symbol. V infinity square. What was the expression? Mu by rho v naught delta beta. Mu by rho v naught is now v infinity actually, delta and beta, right? This is what is going to give us alpha. That is what is we're going to use here. Now equating them, we are going to get how alpha. So if I tell you the value of beta, that beta is this value here. See, just a different expression. Okay, so I'm going to give you these two values, and then you can equate them. You can get how delta varies with x. That's what you will get, right? Just a different expression here, just a different relationship, because it's turbulent flow now. And then we can get friction factor at any x. Friction factor at any x, we can calculate, integrate that over L, and we can get friction factor as 0.072 RE L raised to 0.2 divided by. Okay, combining. So if plate is more than 20 centimeters, this particular example for water, we said it's about 20 centimeters, flowing at 1 meter per second. This is V infinity. So if it is more than 20 centimeters, say it is 1 meter long plate. So first 20 centimeter is laminar boundary layer. 20 to 100 centimeters it is turbulent boundary layer. So I have to combine them. So if you combine them, this will be an expression for overall friction factor, which you can use all the time for any application, for flat plate application, of course. Whenever, one word of caution, whenever boundary layer is separating, right, one word of caution, let me put that. You see, delta by L is small. Whenever boundary layer is separating, we call boundary layer separation. I'll just show you some profile, which we'll talk about it later. Yeah, so suppose boundary layer separation is happening here, right? Now delta by L is not small. So this analysis is not applicable for delta by L large. Whenever boundary layer separates, it is applicable only for places where boundary layer separation has not happened, right? Where boundary layer separation has not happened, it is nice and sticking to the plate, right? You can use this expression. Wherever boundary layer is not separating, it's only for flat plate. Okay. So whatever we have discussed so far is in this book, Fluid Mechanics 7th edition, White's book. We are discussing from chapter 7. It is section 7.1 to 7.4. And for homework, you can try these problems. 7.8 at the end of the book, 7.8, 7.10, 7.26. Okay, do this. Now remember this problem that we have done, drag force on this of this cylinder. Now try this problem in context of this one Karman integral equation. What is the integral equation that you have to do? First take control volume. That's the ABCD. That's what I have already told you, that ABCD is the control volume. Now do mass balance. Mass in, rate of mass coming in, rate of mass going out. Rate of mass going out is small because there is a dip in the velocity. Mass must be going out. Write it as some dm by dx into w, whatever you like. Now do momentum balance. Momentum in, momentum out. Momentum out because of the flow going out. That flow going out as a momentum, it is carrying at a velocity u, capital U, free stream velocity, just like it was carrying momentum based on momentum balance. It was taking momentum based on velocity at the edge of the boundary layer. That was v naught. In this particular case, it is u. Okay. So momentum in, momentum out, momentum out, momentum out. That must be the net force on this object. Do this problem in context of this one Karman integral equation. Okay. And you should be able to get it very easily now. Okay. Yourself. Okay. Again, point I'm trying to make is that we had used microscopic balances to get all these things. And remember, I told you about CFD. So whatever we have done so far, whatever we have done so far, these two parts 6 and 7, we have been able to calculate all the macroscopic things that we had wanted to do using computational fluid dynamics. Let me just show you some examples. Okay. These are results from literature. People have done this. Okay, you wanted pipes and fittings. You wanted head loss coefficients in pipes and fittings, right? This is a CFD simulation of a globe valve. You see, velocity comes in, liquid comes in, it goes through this narrow channel. There are vortices that are generated here. That gives you a head loss coefficient. Orifice meter, C0 we wanted 0.6, right? Velocity comes here, flow goes here. This is the velocity, high velocity here. Vortices are formed here. You can calculate orifice discharge coefficient. Bend, we had got head loss coefficient on the bend. This is a velocity profile. Velocity comes in here. Red regions are high velocity regions. In all these cases, red regions are high velocity regions. And you see that velocity is going like this. That leads to a recirculation region here, recirculation here. That gives you a head loss. You can calculate that by CFD simulations. Pumps, these are velocity fields. Red is high velocity. These are pressure fields. Blue is the low pressure, red is the high pressure. You can calculate the head versus flow curve for a pump based on CFD simulations. We don't need experimental data. Can be calculated from microscopic balances. Lift and drag forces. Flow past a sphere. You can calculate how boundary layer separation. These actually people have calculated. This is for a golf ball. This is for a cricket ball. You see how asymmetric the boundary layer separation is. That leads to a force in this direction. Flow is turbulent here. Boundary layer flow is turbulent here. Now you know what it means. Boundary layer flow is laminar here. Boundary layer separation is faster. Boundary layer separation is delayed. Leads to a force in this direction. Aerofoil. This is the pressure distribution around airfoil. Pressure at the bottom part of the airfoil is large. Top part it is less. There is a net pressure force causing a lift in the upward direction. These are vortices behind balls, a smooth ball and a rough ball, golf ball. You see, flow has become turbulent. Laminar, boundary layer has become turbulent. It can withstand adverse pressure gradient better. It can withstand adverse pressure gradient better. boundary layer separation is delayed. You can see how these vortices, these are all vortices by the way, vortices, something called as vorticity, that is what is plotted. Red is a positive vorticity, blue is a negative vorticity, so that's what it is plotted. You can do it for process simulations, process equipment, stirred tanks, mixing, how it happens, the velocity fields for different impellers. You can do cyclone separators. We talked about that when we were talking about flow of particles, terminal settling velocity. Exchangers, heat exchangers. So velocity fluid comes in, goes out. As it flows, it gets cooled or it gets heated. Everything can be predicted from CFD simulations, which means everything can be calculated by solving these equations. Solving these equations with turbulence model. I don't need empirical expressions for head loss coefficients. I don't need empirical expression for V's discharge coefficient. Everything can be calculated. Ventilation systems in offices, homes, like a classroom, how the temperature field is in a classroom. This might not be very interesting, but when you talk about hospitals, this is how the air is flowing around two patients. One patient is here, another patient is here. How the air is flowing around these two patients. That's important because you want to keep those patients isolated. A pandemic situation, you want people to be isolated. You don't want people to get infected from one another. Okay, CPUs, heat management in computers. This is a temperature field. This is the velocity field coming out of the fan. Okay, you can see how thermal management can be done. Safety and environment, is like a fire. Suppose a fire is there, how the temperature spreads. Suppose there is a wind in some direction, how the temperature will profile will look like, whether there is any danger to the subsequent equipment that is here, or there is a dispersion, there is a pollutant that is being released, how that will get dispersed, which area will be affected, how the wind pattern around the buildings will influence the dispersion. Everything can be calculated from the microscopic balances. Sports, CFD simulations for sports cars. That's how people design racer cars. That's how people design the headgear. That's how people design the bikes. This person is running in the downstream. He is running directly in the flow field affected by the presence of this bike person. How his drag is influenced by this person. Okay, that has a very important bearing on their performance. Medicine, this is a flow of blood in in an artery, different branches, different portion flow is going. Inhalers, stents, PIV measurements, these are actual measurements and they're actually simulations. Okay, flow, how the flow of blood happens in a stented artery. So there is a blockage and a stent has been put to expand that artery, and how the flow occurs. Point that I am trying to make is knowing Navier-Stokes equations, knowing how turbulence can be calculated, how turbulence can be modeled. We can calculate everything, whatever is required, we can calculate. We don't need these empirical equations that we have used in the first 5 parts. We have used so much empiricism, friction factor versus Reynolds number, CD versus RE, C0, valve coefficient, discharge coefficients, head loss coefficient, all those things. I just gave you head versus flow relationship for the pump. I just gave you an experimental value, but now all those can be calculated from CFD simulations by solving this equation. That's the beauty and the power of microscopic balances. You can get any macroscopic property from a microscopic balance. You can do that for yourself. This finishes our momentum transfer part, and then we will use all this for mass transfer part. So one take home message: microscopic balances. And if we can solve these microscopic balances, Navier-Stokes equation for laminar turbulent flow using turbulence model, we can calculate anything and everything that we want. I just give you some examples because they were simple enough to do in class, but at the end I showed you all kinds of examples which people have done by simulating, numerical simulations, computational fluid dynamics. That's the power, that's the beauty of the microscopic balances. So we are done with the momentum transfer part. Let's stop here.